Every 40 seconds, someone in the United States has a heart attack. Globally, ischemic heart disease kills more people than any condition on Earth, claiming over 9 million lives annually and contributing to over 15 million cardiovascular deaths annually. Modern medicine can restore blood flow within hours, but once the heart muscle dies, it is replaced by stiff, non contractile scar tissue that no existing drug, device, or procedure can reverse. A third of the survivors develop heart failure, a progressive condition with a 5-year mortality rate approaching 30%. And currently, there is no FDA approved therapy that regenerates this lost cardiac tissue. My project tackles exactly that gap, as I have built a fully automated computational pipeline that takes a patient's sparse clinical data, constructs a patient specific 3-dimensional model of the left ventricle, which is the chamber most commonly devastated by a heart attack, simulates its biomechanical and electrophysiological behavior, and then deploys a transformer based artificial intelligence model that I developed called HydraBERT to inversely design a personalized injectable hydrogel, further optimizing polymer chemistry, mechanical stiffness, degradation rate, electrical conductivity, injection location, and coverage extent, all in under 37 minutes per patient. And every single patient's heart function improved from heart failure to clinically recoverable categories with a 100% therapeutic success rate confirmed by both AI prediction and full finite element simulation across over 85 therapeutic thresholds. My name is Krishiv, and this is my research. When a coronary artery occludes, cardiomyocytes, which are the contractile muscle cells, begin dying within minutes. A typical transmural infarction kills approximately 1 billion cells, and the adult human heart regenerates fewer than 1% of these cardiomyocytes per year. So that loss is functionally permanent as we know it. The dead myocardium is replaced by a dense collagenous scar with an elastic modulus of roughly 55 kilopascals, compared to the 8 to 15 kilopascal threshold for healthy myocardium. This stiff, non-contractile scar region creates a mechanical mismatch as by Laplace's law, wall stress sigma equals pressure times radius over twice the wall thickness. As viable tissue thins and the chamber dilates, stress escalates in the border zone, driving progressive adverse remodeling towards heart failure with a reduced ejection fraction. Now let's go into the two frameworks that are inherent in my research. Framework 1 is a fully automated pipeline that transforms sparse clinical cardiac data into simulation-ready 3D finite element models. The input comes from the Sunnybrook cardiac MRI dataset, where left ventricle geometries are encoded as qubit Hermite meshes with approximately 60 nodes per patient. These store not just positions, but partial derivatives capturing surface curvature, which standard tools ignore entirely. From those 60 nodes, I reconstruct a smooth surface through Delaney triangulation, 3 iterations of loop subdivision where each triangle splits into 4, amplifying 60 faces into roughly 3,840, and Laplacian smoothing to remove artifacts with less than 1% volume shrinkage. Every single input mesh contained topological defects, non-manifold edges, degenerate faces that all crashed during volumetric meshing. I developed a 7-operator sequential repair algorithm to restore them, and through this I discovered what I call the boundary quality principle. Surface mesh quality fundamentally dominates volume mesh quality, and no amount of interior optimization can compensate for these defects on the boundary. The repaired surface is then filled with tetrahedra using FTET wild, with all geometric computations accelerated 50-fold through numbajit compilation. The final output is 60 nodes becomes 3.66 million tetrahedra across 10 patients, with 0 inverted elements, 2 to 5 minutes per patient, and fully automated. Now, a geometric mesh alone cannot simulate cardiac function. Every element needs fiber orientation vectors, which govern both electrical conduction and force generation. I solved the Laplace equation across the mesh to create a smooth transmural coordinate mapping every point's dead through the wall, then assigned fiber angles following the Streeter model, with positive 60 degrees at the endocardium, rotating linearly to negative 60 degrees at the epicardium. A key contribution here was the topology-based boundary extraction. The standard approach uses percentile heuristics and produces only 10% mean transmurality, compressing fiber rotation into a tiny fraction of the wall. However, my method identifies boundary faces from mesh connectivity alone. Any face belonging to exactly one tetrahedron is defined by a boundary face. This produces 52% transmurality, matching published anatomical values, a 5-fold accuracy improvement. Section 5 is where I compute patient-specific wall stress and identify where to actually inject the hydrogel. The classic law of Laplace assumes the heart is a sphere with uniform wall thickness, both grossly wrong for a real left ventricle. I developed a modified formulation that replaces those assumptions with local wall thickness derived from my Laplace transmural gradient and local curvature extracted from the shape operator at endocardial vertices, which captures how the surface bends in each principal direction. The result is a wall stress map that reflects the actual patient-specific geometry rather than an idealized sphere. To measure distances along the heart surface, I implemented the heat method, which is an elegant algorithm that computes geodesic distances through three sequential linear solves rather than explicitly tracing shortest paths. I then combined wall stress and geodesic distance into a multi-objective scoring function that jointly optimizes for four criteria: proximity to the border zone, high wall stress regions, mid-wall transmural depth, and border zone membership, with core scar excluded because it lacks perfusion and a 15 mm minimum separation between sites. What makes this novel is that no prior framework integrates all four of these components. With simulation-ready models, I ran three categories of physics simulation. For electrophysiology, I used OpenCart with the 10 Tusker-Panfilov ionic model, 19 state variables running 130 simulations across 10 patients, including S1, S2 arrhythmia vulnerability protocols. The result was zero inducible reentrant circuits at baseline, confirming a clean electrophysiological substrate. Healthy tissue conducted at 0.316 meters per second, SCAR at 34% of normal. For biomechanics, I used FEBio with the transisotropic Mooney-Rivlin constitutive model with active fiber contraction. Full dynamic cardiac cycle simulations completed for all 10 patients with zero solver divergence. Ejection fraction was 36.6%, consistent with heart failure with reduced EF. Border zone stress was 1.67 times healthy tissue, confirming the biomechanical driver of adverse remodeling. I then swept 1,400 hydrogel configurations per patient, 14,000 total simulations varying stiffness, connectivity, and injection pattern to generate the training data for the AI model. Now moving on to Framework 2, HydroBERT. HydroBERT is a three-stage deep learning pipeline for inverse hydrogel design. Stage 1 is a supervised multitask learning. The foundation is PolyBERT, which is a transformer pre-trained on 100 million polymer small strings that produces 600-dimensional chemical fingerprints. Rather than fine-tuning all 86 million parameters and risking forgetting, I applied low-rank adaptation, adding only 1.18 million trainable parameters, a 97% reduction. The full architecture fuses three inputs: polymer chemistry through PolyBERT, formulation parameters through an MLP, and patient cardiac features through a separate MLP. These converge in a cross-modal fusion transformer, with four layers, 8 attention heads, producing a joint representation that feeds 3 prediction heads: ejection fraction improvement, therapeutic classification, and safety scoring. Training using 447,480 samples across 16 A100 GPUs. Stage 2 is reinforcement learning. The frozen stage 1 model becomes a reward function for the proximal policy optimization. The RL agent selects polymers, sets formulation parameters, and chooses coverage patterns. Over 40 billion transitions across 2,000 parallel environments, the optimal design rate rose from 24% to 78%. Now, Stage 3 generates 10 million candidate designs per patient. 60% PPO guided, 20% systematic grid, 20% Latin hypercube for diversity. All 10 million are scored at 100,000 designs per second, then filtered through a 6-stage cascade: safety screening, reward ranking, diversity selection, physics surrogate pre-screening, full dual solver simulation, and final Pareto optimal clinical selection. The cascade converges from 10 million to one optimal design per patient in approximately only 37 minutes. The pipeline was validated across more than 85 distinct metrics spanning every stage, from mesh quality and fiber accuracy against published experimental data through ML generalization and physics simulation agreement to therapeutic outcomes and statistical significance, with every single metric meeting or exceeding its target. All 10 patients passed all 5 hard clinical thresholds with 100% therapeutic success. Ejection fraction improved from 36.4% to 45.5%, crossing the critical heart failure boundary, confirmed at p less than 0.001 with a Cohen's d of 1.87. This pipeline is the first end-to-end system that can take a patient's clinical data and produce a personalized hydrogel prescription validated by physics and optimized by AI. It compresses what currently takes 10 to 15 years of iterative experimental development into days of computation, evaluating 100 million designs in 32 hours rather than testing one formulation at a time in animal models. The entire workflow is automated. It dramatically reduces the need for animal testing, and the approach isn't limited to cardiac hydrogels. The same inverse design philosophy could be applied to biomaterials for spinal cord injury, brain tissue engineering, or wound healing. All the code and data have been released open source. I would like to extend my gratitude to the Davidson Institution for their dedication to supporting young innovators and for the opportunity to apply to the Davidson Fellow Scholarship. Thank you.